Hello, welcome back. In this last lecture of this week and also on the topic of greedy, we will talk about a very interesting greedy algorithm, Huffman coding. What is a code and what is encoding? We know for modern electrical computers, transistors are used to represent the two stable states, on and off. That is the reason why everything stored and run on a computer is represented using binary strings, 0 and 1s. These include text, audio, images, and videos. Here is an example of encoding letters using binary strings. We can assign an unique binary code to each letter of the alphabet. The words and sentences can be encoded using bit strings, such that they can be stored, operated on, and transmitted on computers and networks. See that if we can use shorter bit sequences to encode the letters, we can have shorter representations, thus reducing the number of bits needed to store the information while maintaining full recoverability is a vital problem, especially for information communications. Compressing a file reduces the time required to transmit it. The challenge associated with data encoding and compression is to represent the information as compact as possible without losing any of its information. Information encoding has a large collection of applications, including ensuring reliable and fast data transmission, encryption, and compression. For instance, American Standard Code for Information Interchange, ASCII, is commonly used for text encoding. Each character is assigned a unique 8-bit string. We know that there are 2 to the power of 8 this many unique strings with 8 bits, so that's a capacity to represent 256 different characters. ASCII uses fixed-length encoding and certainly does not seem to be optimal. We know that certain letters in English appear more frequently than others, such as A, T, or S. So the idea is, can we use variable length coding? So more frequent letters use shorter representations. Here is an example where we compare fixed coding and a variable length coding. For word Hawaii, the 4-bit fixed-length representation is 24 bits long, while for the variable length encoding, where shorter encodings are used for more frequent characters, Hawaii only takes 14 bits as its total length. I hope you get the idea now. Another variable length coding example is Morse code. This is a fading technology, but can see lots of references in pop culture. There are 2 symbols in Morse code, dot and bar. Letters that are very common are assigned shorter codes. E and T, for instance, only have 1 symbol. Other common letters such as A, I, M, and N have only 2 symbols. Morse code was typically sent over radio manually. It uses short pause between symbols and long pause between words. So when we hear dot 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 dot, we know it is 2 I's instead of 4 E's or 1 H. So what is SOS in Morse code? That'll be dot dot dot, bar bar bar, dot dot dot. Okay. Thinking about computer code, we only have zeros and ones, so no short pauses nor long pauses. So how do we know the end of a word and how to avoid the ambiguity? Now we will see a property, prefix, that is required for bit codings. It states like this: a coding satisfies the prefix property if none of the assigned encodings occurs as a prefix of any other assigned encodings. When a code satisfies the prefix property, we can decode without any ambiguity at all. As soon as we identify a sequence that has been assigned to a character, we know that is the correct character and we can start to decode the next character. Does Morse code satisfy the prefix property without using different pauses? No. For instance, E, that's one dot, is a prefix of A, F, H, I, and so on. Does this variable length code satisfy the prefix property? Yes. When we see this bit string here, we know 0, 1, 0 represents the letter H. And then 0, 0 is for A. And 1, 1, 0 is for W. And so on. There's no ambiguity at all. We can use a binary tree to visualize a prefix code. For instance, the coding looks like this. We start from the root. If we see a 0, we know it is for letter C. If we see a 1, we get to the right-hand branch. And then if it is followed by a 0, we know we're looking at a letter A. And if that 1 is followed by another 1, we know we have letter T. Every prefix code can be represented as such a binary tree, where the leaves correspond to the characters in the alphabet. Decoding, on the other hand, becomes a matter of starting at the root of the tree and following the branches dictated by the bits. When we reach a leaf, we record the decoded letter and return to the top of the tree to continue. Can you pause the video and decode the bit string 01011? Yes, it encodes cat. When we want to optimize a coding, we want to have more frequent characters higher up in the tree, so they have shorter encodings, and the less frequent ones lower in the tree, so they have longer encodings. This is exactly the idea of HuffmanCoding. Huffman published this algorithm when he was a PhD student at MIT, where he built the code by building the binary tree from the bottom up. It is guaranteed that the coding is optimal and unambiguous. Now let's see how this algorithm works. Please pause the video and read through the algorithm. We will show an example in the next slide. Suppose we have an alphabet S, where we have letters A, B, C, D, E, and F, with their frequencies respectively. We can first sort all the characters based on their frequencies. In the first step, we take the least frequent two characters, A and E, and create their corresponding leaf nodes in the tree, A and E, and we connect them to a common parent node, AE, with a frequency 15. We assign 0 to one branch and 1 to another branch. The order does not matter. Next, we update the table by replacing A and E with AE together. Now we look at the bottom two letters again. So these are C and D. Again, we create two leaf nodes. C and D, we connect them by creating a new common parent, DC, and we add up their frequency. So DC now has a new frequency 17. Then we update the table with CD replacing C and D. Next, we take the bottom two letters again. Now we are looking at AE and F. We add a new branch for F. To the tree AE we previously constructed, we create a new common parent, AEF, with a new frequency 26. Next, we update the table. Now we have 3 characters left. The bottom two are now B and CD. Again, we create a new leaf node for B and connect it with the subtree DC. We create a new common parent node DCB. And we assign 0 to one branch and 1 to another branch. Finally, we have two characters left in the table, DCB and AEF. We can connect them, DCB, AEF. Now there are two subtrees. We connect them by creating a new parent node, DCB, AEF. Now all the original single letters have merged as the root of this binary tree. Now we have completed the tree construction. Last, we can provide a unique code word for each single letter by tracing the binary tree from the root to that character's corresponding leaf node. For instance, if we want to know what's the code word for A, we start from the root and go along the path that can travel to A. So we know A's code word would be 100. Similarly, when we find B's leaf node, we can travel from the root to that leaf node, and then we know B's code word would be 01. Please pause the video and finish the code words for the rest of the characters. Huffman code has the prefix property. In addition, the code word length is inversely proportional to the frequency of a character. Less frequent characters are further away, like D, C, A, and E. More frequent letters are closer to the root, like F and B. So in addition, Huffman code is optimal in terms of providing the most compressed encodings. Now let's see a comparison between Huffman and 3-bit ASCII. Given the frequencies of different characters, if we sum up all the bits needed to represent the entire document, that is, we add up the length of each character times its frequency. In total, Huffman uses 150 bits and ASCII uses 177 bits. Note that the actual ASCII coding uses 8 bits instead of 3. So the real representation will be even longer than 177 bits. Also, this example only includes 6 characters. With larger alphabets and higher frequencies, Huffman coding will show even more clear advantages. Huffman coding is optimal among all prefix code. That is, there is no prefix code that uses a smaller total number of bits than the Huffman code. Now let's formalize the problem of coding optimization. Given an alphabet A, where each letter X has a frequency F, the goal is to find a binary tree T with A's cardinality this many leaves that minimizes this sum. Here, the depth of a node or a letter is the number of edges from the node to the root. In other words, it is the length of a letter's encoding. Now let's look at the Huffman coding algorithm again. Is this a greedy algorithm? Yes, it is. It sorts letters based on frequencies and picks the least frequent 2 letters at each iteration. What about the complexity of this algorithm? Sorting will take a big O of n log n time, and then we can walk through all the characters from the bottom until they all merge together. This takes linear time. So the overall complexity of this algorithm is a big O of n log n time.